I'm going to show you some weird physics. Now, copper and magnets are not attracted to each other. I certainly can't pick up a piece of copper using a magnet. But watch what happens when I bring this copper plate next to the magnet and move the copper plate back and forth. We see that the magnet is both attracted and repelled by this plate. So we want to understand what's going on here. Why does it do this? Now, to start, around any magnet is what we call a magnetic field, such that at any point in space around the magnetic field strength tells you how strong that magnetic effect will be on something. We have to go a step further though. We have to know about magnetic flux. Now, magnetic flux is just the total magnetic field that goes through a certain area. In our case, we're interested in the magnetic flux that passes through the copper plate. This will equal the average magnetic field over the surface of the plate times the area of the plate. So when the plate is moved away from the magnetic field at the plate will decrease, so will the magnetic flux going through the plate. And when the plate is brought close to the magnetic field increases, and so does magnetic flux. If the plate and magnet are stationary, of course, there is no change in the magnetic flux. Now, Faraday's law says that any change in the magnetic flux in a conductor will lead to currents within that conductor. Now, normally we think of current as something flowing through a wire, and that's true. But one can get current in any conductor, even this plate. In this case, the currents within the plate are called eddy currents. Now, any electric current will create a magnetic field in the space around it, just the same as a magnet would. So in the case of the copper plate, if it's moved and the magnetic flux is changing, eddy currents are formed, we're going to get a magnetic field around the copper plate. The polarization, the north-south polarization of the plate will depend on what the direction of the eddy current is. Now, the last piece that we need to know to understand is Lenz's law, which states that the created magnetic field and the north-south polarization of the plate will be such that it will oppose any change in the magnetic flux going through the plate. If you think about it, the resulting magnetic field and the north-south polarity of the plate would therefore need to be such that it will reduce the rate at which the plate and magnet approach and separate. This would reduce the rate at which the magnetic flux changes. Now that we've looked at magnetic flux, Faraday's law, and Lenz's law, let's look at this interaction again. As the copper plate is being pulled away from the magnet, the direction of the magnetic field created by the eddy current attracts the magnet. This will slow down the rate they separate and therefore reduce the rate at which the magnetic flux is changing. The magnet doesn't actually hit the plate, because once it is moving at the same speed as the plate, there will be no induced current and no magnetic field around the plate. Now, when the copper plate approaches the magnetic field of the plate will reverse, repelling the magnet. This will slow down the rate at which they approach, and again will reduce the rate at which the magnetic flux is changing. An odd interaction with some interesting physics behind it. So far we've considered it's the plate that's moving. But with Faraday's law and Lenz's law, it doesn't matter if it's a plate moving or is a magnet moving. So I've changed the setup now. So in this case, I'm going to let the magnet fall towards these copper plates. The question is, what will happen? As you see, the magnetic repulsive force induced in the plates is enough to stop that magnet dead in its tracks. Indeed, this is the principle behind magnetic damping. Thanks for watching.